This is an informative video of electron configuration in orbital diagram by Jon'Tajah Short. First, let's get into some key terms. The first key term being orbitals, which is a region of space where the probability of finding an electron is 90%. Principal quantum number tells us the size of the orbital, using numbers 1 through 7. Angular quantum number tells us the shape of the orbital, using letters S, P, D, or F. Magnetic quantum number tells us the orientation of the orbital. S having only one orientation, P has 3, D has 5, and F has 7. The spin quantum number tells us the spin of the electron, using up and or down arrows. Now for the rules for electron configuration in orbital diagram. Rule number 1. You must first fill the lower energy orbitals before filling higher energy orbitals. Rule number 2. Each orbital can hold a maximum of 2 electrons. Rule number 3. Each electron in an orbital has opposite spin. And rule number 4. For degenerate orbitals, fill each orbital with 1 electron before pairing. Now let's get into some examples so that those definitions and rules make sense. First things first, we're going to start with silicon. So using the periodic table here, you can see that silicon is right here, number 14. So let's block off the rest so that we don't confuse ourselves. Now, when doing electron configuration in orbital diagram, you move from left to right of the periodic table. So we start up here with the H. So you have 1s1 and then 1s2, because as you can see, this is an S as well. So 1s1, 1s2. So you write it as such. 1s, and then up in the exponent, you write 2. Now, if you remember, when we talked about the magnetic quantum number, it said that S had only one orientation. And rule number 2 said that each orbital holds up to 2 electrons. So being that S only has one orientation, that means it can only hold up to 2 electrons, because 1 times 2 is 2. So moving on, we have 2s1 and 2s2. Again, S only has one orientation, can only hold 2 electrons. 1 times 2, that's 2. So now we have to move over to the P's, because again, we're moving left to right, and we can't just come down to 3. So at 2p1, 2p2, 2p3, 2p4, 2p5, and the P's start here for this one. So 2p6. 2p6. Now going back to the orientations, P had an orientation of 3. So out of those 3 orientations, if each of them can hold 2, 2 times 3, that'll give you 6. So that's how you know that this one is full, because all 6 of the electrons for this one was used. So going down to the 3's, 3s1, 3s2, 3s2. Then going across to the P's, you have 3p1, 3p2. And we stop here because we're going to silicon. So 3p2. Now a way you can check yourself to see if you did it correctly is silicon is number 14. Meaning it has 14 electrons. So up here in the exponent, once you add all of them together, you should get 14. So 6, 8, 10, 12, 14. Again, silicon is 14. So you did it right. So moving on to our next example, which is calcium. And calcium is number 20 on the periodic table, as you can see right here. So we're going from up here all the way to down here while moving left to right. So following the same steps that we did with silicon, you have 1s1, 1s2. And you write it the same way, 1s2. Then you go down to the 2's, 2s1, 2s2, 2s2. Then you go over to the P's. 2p1, 2p2, 2p3, 2p4, 2p5, 2p6. So 2p6. Then you come down to the 3's. 3s1, 3s2, 3s2. Go over to the P's. 3p1, 3p2, 3p3, 3p4, 3p5, 3p6. So 3p6. Then you go down to the 4's. 4s1, 4s2, and you stop here because we're going to calcium. So 4s2. And again, the way to check yourself, you know it's 20, so you add them up. 6, 12, 14, 16, 18, 20. You did it right. The next example, iron. And iron is right here, number 26. So again, same steps. 1s1, 1s2, 1s2, 2s1, 2s2, 2s2. Going across to the P's. 2, P1, P2, P3, P4, P5, P6, 2, P6. Come down to the 3's. 3s1, 3s2, 3s2. Go over to the P's. 3p1, P2, P3, P4, P5, P6, 3p6. Then you go down to the 4's. 4s1, 4s2, 4s2. Now here's where it gets a little tricky, because when you get to here, it starts with 3 D's, because the D's lag by 1. So you have 4s, then you have 3 D's, then you go 4p. And then when you go to the next level, it'll be 5 S's, then 4 D's, then go back to the 5 P's, and so on and so forth. So 3D1, 3D2, 3D3, 3D4, 3D5, 3D6. 3D6. Now, D had an orientation of 5. And each orbital can hold up to 2 electrons. So 5 times 2 is 10. However, you have 6. So that's how you know that this one isn't full. But again, to check your work, 26, 6, 12, 14, 6, 12, 18, 20, 22, 24, 26. So you did that correctly. Now for our last example. RE. And RE is right here. Number 75. So we got a good little ways to go. So 1s1, 1s2, 1s2, 2s1, 2s2, 2s2. Over to the P's. 2p1, 2p2, 2p3, 2p4, 2p5, 2p6, 2p6. Come down to 3's. 3s1, 3s2, 3s2. Go over to the P's. 3p1, 3p2, 3p3, 3p4, 3p5, 3p6, 3p6. Come down to the 4's. 4s1, 4s2, 4s2. Again, this where 3D starts. So 3D1, 3D2, 3D3, 3D4, 3D5, 3D6, 3D7, 3D8, 3D9, 3D10, 3D10. And this is now full because D had an orientation of 5. 5 times 2 is 10. But coming back to this, now 4P, 4P1, 4P2, 4P3, 4P4, 4P5, 4P6, 4P6. Coming down to the 5's. 5s1, 5s2, 5s2. Then again, the D's lag by 1. So these were 3 D's, meaning these would be 4 D's. So 4D1, 42, 43, 45, 46, 47, 48, 49, 40, 4D10. And then you go back to the 5's. 5P1, 5P2, 5P3, 5P4, 5P5, 5P6, 5P6. P, 6. Then you come down here to the 6's, 6s1, 6s2, 6s2. Now, here's where things get a little tricky, because if you look here, you see it goes from 57 to 72. But you can't just jump here. There are numbers in between, which is where the F comes in. Let me move this up. I'm sorry. This is where the F's come in. So from 57, this is where 58 starts. And you have to take all of these numbers into account. So that's where you get the 4F. So 4F. And if you remember, F had an orientation of 7. And each one can hold 2. So 7 times 2 give you 14. So 4F, 14, takes care of all of these. Then you can come back up to right here, making the next, making the next one 5D. 5D1, 5D2, 5D3, 5D4, 5D5. 5D5. And you are done with the electron configuration for that one. Now we're going to move on to the orbital diagram. So doing the orbital diagram for each is easy because it's the same steps, except using exponents, you'll be using up spin, down spin, which if you remember from number 4 in our rule, it said for degenerate orbitals, fill each orbital with 1 electron before pairing. And then if you remember from our key terms, the spin quantum number told us the spin of the arrows. So starting with silicon, once again, we're going to just take this electron configuration and then convert it to the orbital diagram. So you'll still keep the 1s, same 1s, but instead of using exponents, you use arrows. So you do up spin, arrow, and down spin, arrow. And you must always fill lower level energy orbitals before filling higher energy orbitals. So moving on to 2s, once again with the arrows, and you always do 1 up spin arrow before a down spin arrow, always. Now we're moving on to 2p, and again, p has an orientation of 3, so you'll write p 3 times. No matter what number is attached to it, whether it be 3p, 4p, 5p, you always write the p 3 times. And by the way, when you have a block of the same thing like this, this is a degenerate orbital. And you always have to do 1 before going back and pairing. So you would do an up spin arrow for each of these before going back and doing a down spin arrow. And you know that you have to go back and pair them doing a down spin arrow because we're working with 14 electrons. This is not 14. 2, 4, 6, 8, 10. You still have 4 more to work with. So after the 2 P's, then you go over to the 3S. 3S, only 1 orientation, so up spin arrow, down spin arrow. Then 3P. And again, every time you have a P, you have to write it 3 times. You have to. No exceptions. Now, filling them up, you always have to do 1 up spin arrow in each of them before pairing them with a down spin arrow. However, we only have 14 electrons to work with. So 2, 4, 6, 8, 10, 12, 12, 13, 14. And we are done with the orbital diagram for silicon. Moving on to calcium. Same thing. You take what's already here and you turn the exponents into arrows. So 1s, up spin arrow, down spin arrow. 2s, up spin arrow, down spin arrow. 2p. And you always write the p's 3 times. Never forget that because they have an orientation of 3. Do it up spin arrow before pairing with the down spin arrows. So up 1, up 1, up 1. Go back down and pair them with a down one. Now we're moving on to 3s. 3s. Again, up spin arrow, down spin arrow. 3p. Again, write it 3 times. No matter which number is attached to the p, you will always write it 3 times. Now you want to up spin all of them before you down spin all of them. So up 1, up 1, up 1, down 1, down 1, down 1. And the last one is 4s. 4s, up spin, down spin. Now, we want to count them because we're going to 20 for this one. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. You use up all of them. Next, iron. And it doesn't matter how many P's is here. You always write them 3 times. Same thing for now. We're going to get into the D's. D's has an orientation of 5. So when we get down to 3D, we'll have to write 3D 5 times. So let's do it. 1s, up spin arrow, down spin arrow. 2s, up spin arrow, down spin arrow. 2p, you will write that 3 times. Up spin arrow for all of them before going back and pairing them with a down spin arrow. Then you want to move on to 3s. That's the next one. Up spin arrow, down spin arrow. Then we're moving on to 3p's. Again, it's a p, so you write it 3 times, no exceptions. My apologies for that one. You always do up arrows for all of them, then go down and do the down arrows. Next, 4s. Up spin arrow, then a down spin arrow, then 3D. And again, D had an orientation of 5, so you write this 5 times. 4, 5. And you always do 1 up spin arrow for each of them before pairing them with a down spin arrow. But for iron, we had 26 electrons to work with. So 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 21, 22, 23, 24, 25, 26. And we are done with the orbital diagram for iron. Now let's get back into that really long one. Same rules apply. 1s, up spin arrow, down spin arrow. 2s, up spin arrow, down spin arrow. 2p, 1, 2, 3. Up spin arrow, up spin arrow, up spin arrow, down, 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 to make sure they're all paired. Then you want to go to 3s, up spin, down spin, then 3p, 1, 2, 3, up spin, up spin, up spin, down spin, down spin, down spin. They're all paired. Now we're going to go to 4s, up spin, down spin, 3D. So you have to write it 5 times. 1, 2, 3, 4, 5. And you want to up spin all of them first, then down spin to pair them. Now after 3D, 4P. Again, no matter what number is attached to it, no exceptions, you always write it 3 times. Up spin all of them first, then you down spin. Then you have 5s. Up spin, down spin. I'm running out of a little space, so I'm going to go down below. At the 5s, 4D, again, no matter what number is attached to it, whatever orientation that is, that's how many times you write it. And being that D has an orientation of 5, we're writing 4D 5 times. Up spin all of them first before down spinning them to pair. Down spin, down spin, down spin, down spin, down spin. Then you have 5P again. Does not matter what number is attached to it. Up spin, up spin, up spin, down spin, down spin, down spin. Then you have 6s. Up spin, down spin. Then you have for F. Now again, F had an orientation of 7. So we will be writing for F 7 times. 1, 2, 3, 4, 5, 6, 7. And we're going to be up spinning all of them before down spinning. Now we pair them with the down spin. And last but not least, we have 5D, which will be written 5 times. And we will upspin all of them before downspin them. However, when working with RE, we had 75. So 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32, 34, 36, 38, 40, 42, 44, 46, 48, 50, 52, 54, 56, 58, 60, 62, 64, 66, 68, 70. Now we're going to 75, so 71, 72, 73, 74, 75. And because we used up all the electrons, there's no need for us to go and downspin all of them because this is the full 75. And so that is the orbital diagram for this one. And that concludes our video for electron configuration and orbital diagram. And I really hope this video was as informative as I intended it to be.